Good morning, everybody, and thank you for joining our webinar today, Timber to Steel Connections, Theory, Experimental Campaign Solution, and R&D. My name is Chris Chukagian. I am the marketing account here for Rothablas in North America. I just wanted to run through at the beginning a quick reminder. If you have any questions at all throughout the presentation, we'll be answering them towards the end. If you're on a computer, on the top bar, you should see a button for Q&A. And if you click into there, you can post questions. If you're on a phone, in the bottom right-hand corner, there's 3 dots that you can click to open up the same menu, find the Q&A, enter it, and then type your questions in there, and we'll answer them at the end of the presentation. Without further ado, I will let our speaker, Alessio, take over, introduce himself, and lead the presentation.
Okay, great. Hi, Chris. Thank you very much. Let's go straight into the topic. Today we speak about timber to steel connections, a very hot topic in timber buildings. I'm Alessio Maffeo. I'm a consultant, so it means that I am a timber engineer, a designer, and also consultant for Rothablas in terms of helping designers to find the right solutions. So this topic is pretty hot because what we want to say is that generally there are positive and negative sides in the world of timber. Usually online, on LinkedIn maybe, or online, we only look at the positive aspects, right? We look at all of these nice ideas and concepts behind a timber building: sustainability, speed of installation, and so many other nice things. But at the same time, there is also a dark side of the moon. So we like to start in this way. There is also a dark side of it. And what is the dark side? The dark side is that in many construction buildings in timber, sometimes you go on site and you find this situation. So what do we notice here? We notice a few issues. We notice different types of screws connected to the same bracket. We notice, of course, a lot of water on the ground, no protection of the timber. We notice these screws up here not installed in the right way. They are inclined, so we can imagine that we could have issues on this side of mold, issues with the type of connectors. It looks like some people, they just took the first connector that they had and they just installed it. And for example, it's not possible to use flat head screws like this one on a steel plate. So this is the reality of the construction site. And now we have to start to understand it and to analyze it and to see what is the meaning of this. Like we just said, we could have wood decay. We could have also corrosion on the steel elements, and also finally could lead to the failure of the fasteners. Usually, so if we look at the swelling of the timber, so since we have all of this water absorbed by the timber element, it's easy to see and to understand that most likely timber will try to expand, to swell, and then push against the plate. In many cases, we will see during this presentation, we will see that it's also very important the fact that we are going, in some cases, the installer is going to insert and over torque the fasteners. This is also a not positive aspect. And also, as we just saw, it can also happen that there are a misalignment between the screw and the plates. Generally, we design our connectors in a way in which the stress acting on the fasteners is of course lower than the design resistance. But actually, we know that timber is a biophilic material. It's a material, of course, that has grown in the nature, and it is a capillary material. It's a material that has a feeling for water, of course. It's a material that has different behavior in swelling and shrinking based on the direction to the fiber. And we see this also from the fact that there are plants living off the water content in the air even. So of course timber and plants in general, and plants in general are a very biophilic material together with water. Generally, generally, let's say the consensus is that up to 30% of the water moisture. So if the moisture is below 30%, it means that the water is bound water, it's called. So it means that the water is still in the structure of the timber fibers. Above 30%, it means that now the water is not anymore contained in the fibers, but it is actually floating, let's say, floating in the timber member, not anymore only in the fibers. And this explains this concept a bit better, right? 100%, there is water both in the fibers and also in the empty areas. 30% is only bound water. 10% of moisture, we have a bit of water only in the structure. 10% of moisture, as you maybe already know, it is more or less the moisture that we want to have when the timber is delivered on site. Usually, supplier can deliver at 12% moisture content on site, to site. We never want to accept a timber that is above 12% at the delivery. Timber actually has different expansion rates. So these are percentages. So these are actually adimensional numbers explaining the change in dimension for each percentage of moisture content change. So this is the elongation. So all of these values are the elongation of the timber member per each percentage point of moisture content of change. For solid timber, we actually differentiate between the radial and tangential, and for glulam, we keep this number for the longitudinal one and this number, which is actually 20 times higher for the radial and tangential. Just a quick animation. You see, we can see this together. And this one on the left is a graph of the moisture content on relative humidity. So of course, changing the relative humidity on the x-axis, we will have different moisture content on the vertical axis. What's happening here? So this is a graph again explaining the relation between moisture content and relative humidity of the air. So this humidity on the x is the water content in the air. So is, for example, in this room here where I'm in now, it could be around 60%, 50%. Generally, our normal conditions are around between 30%, let's say, and 60%, so, which means that timber has a moisture content of around between 8%, 10%, 12%, maybe a bit less, but more or less we are around this, let's say, 8, 10% of moisture content. As soon as we go with a too low humidity or a too high humidity, there's a very steep slope here, especially for the high humidity. So we never want to stay in these red areas. These, in fact, are also the reason why we usually differentiate between service classes, meaning the fact that sometimes if you go in the service class that is external, exposed to the environment, you can easily have a very big swell. And actually, this means that also on connections, we have to apply some safety coefficients. If we make this, this example, now we can try to see and what happens to this beam. So it's a 13 feet beam. The base is 4 inches and 3/4. The height is 778, and so on. Let's play this. You can tell immediately that the longitudinal swelling is not as big as the tangential swelling, which actually is it's actually the highest one. So we go from a base of 4 3/4, we increase by 1/8 of an inch. From our height, we increase by 3/16 of an inch, which is actually something that we cannot neglect. It's something that we start to see. So it's a swelling of timber that we can start to see if we apply this theory. This happens. The idea behind this is that we have a 10% moisture change. So with a 10% moisture change, the longitudinal direction is not the most critical one, because the coefficient that we saw before for each percentage of moisture change was pretty low. The most critical ones are the radial coefficients, which brings to a, let's say, which takes us to a pretty high dimensional change. This will be critical, of course, when we start to have a timber element constrained between a steel element. So this is something that we never want to do. So again, imagine the first image: a floor full of water, and then we have an element constrained between two pieces of steel. This is something that we do not want to have. This render on the left, so this image actually is taken from a real project, the one that we just saw before. And again, what happens is that what will happen is that with water, so you see these screws here on the flat slab, most likely we will start to get a lot of swelling, and then the compression against the plate, and then the pull force there. What is funny now to see, not so funny, but what is interesting to see is now to try to see what is the impact of this amount of stress. So how big, let's say, how big can the pressure made by swelling be? As you maybe already know, in the past, the Egyptians used to, but this is something that sometimes we also do today, they used to use timber pieces inserted in the rock, and then they would pour water on the wood itself to cause it to break. So you see here the signs of these opening points. Let's make an example now then. Imagine to have this surface, so let's say it's a small surface, something around 4 inches by 4 inches surface, and we have a 10% change in moisture content. Applying this standard, which is a standard for timber, we cannot replicate the whole calculation now, but if we apply this calculation, that you can maybe then take a screenshot and follow more slowly. In theory, this piece of steel, which again is a 4 inch by 4 inch on a piece of timber with a 10% moisture change, in theory, following this calculation, we get to this amount of pressure. So this is a spring system. It's a sort of spring system. So basically, we find the Young modulus of the timber itself. We multiply it by the swelling, so by the space swelling, and we get around 12,000 pound force, which is actually it's surprising, right? We are around more or less the weight of an elephant, or maybe the weight of 3 medium cars. So the question is, what do you think? Is it possible that, does it make sense that just a small plate of steel can push this much? So it means that on our construction site, that we saw at the beginning, we have our timber element, the water is pushing. It means that we should have in theory this load. Of course, this is just a theoretical calculation. We cannot say that this is actually the load that we're going to have exactly, but it's a good let's say it's a good estimation. Now we will see that we also made a real case. So we took a piece of glulam, 4 by 7 inch by 4 by 7 by 9.5 inches. So you see it here on the left. It's a piece of timber with load cells and everything constrained by this threaded rod with plate and counterplate. So it's a really a compressed element, and we put it in water. So you put it in water and you wait for the shrinkage. Sorry, you wait for the swelling of timber to increase the size of the timber element, and then it means that on the load cells we will be able. So the load cells are inside here at the top. It means that we are going to be able to measure the pressure made by this glulam piece. You see it here on the left in the bucket. Okay, some more examples. The load cells connected with wires, the pieces in the water. Nice phenomenon. You see the glue starting to block the passage of water in the timber element. And what happens after 72 hours, it's a bit surprising. What happens is that we start to have in 72 hours, something around 1800, again, pound force. After one day, we had this amount of push, so we are more or less 50% of the final one. And then finally, after 3 days, almost the weight of a small car, we could say, the weight of a small car could be. So this is actually, it's surprising, right? So we have the weight of a single car pushing on this small plate that we saw before. It was a 4.7 by 4.7 constraint between plate and counterplate. Just putting it into water after 3 days, we get this pressure on the load cells. So we understand that timber we want to swell, and if we block it too much, we're starting to see we could see some issues. Then we made another experimental campaign, and this campaign was made using a thin plate, again with a screw. This element here is the top of the screw, and then also with a thick plate, and also with a thick plate plus a resilient material. Usually this is an acoustic profile. It's an acoustic profile that sometimes we can also start to think about using it for this buffer element. So we want to have it to use it as a sort of element to absorb some of the compression made by the water, by the timber. Again, this is another campaign, very similar setup, but there is not anymore the plate and counterplate with a threaded rod. But in this case, we want to measure and see after a few days what happens to the connectors. So the benchmark is a screw connected, actually two benchmarks, a thick plate and a thin plate. And then we want to see what is the effect of an improper installation, so with an inclination, and also with an over torque. So if we drive the screw too fast and we smash the head against the steel plate without stopping before the plate, it means that we are over torquing the fasteners. And then also we can see what happens with a a damping solution, so with something to absorb the compression. So it's a sort of intermediately stiff element that we can put, that we can install between timber and steel, and then see how this goes. What is the final result? After 6 weeks, we have the thin plate. You see the timber moving freely, so the timber can actually move and bend the plate. With a thick plate, this is not possible. So immediately you start to think that, okay, when I have a thick plate, it means that all the compression will go against the screw, against the plate. It's not possible to modify and to bend the thick plate like you bend the thin plate. And with xylophone, so with the acoustic profile, the situation, we see that it is being compressed. We see it also by this picture. So this is a zoom. It's a zoom image of this detail of the picture before, right? In which we see that actually effectively we have a compression layer. So this is positive because we have something that is able to absorb some of the compression. Now, this is the right installation. This is a correct installation. So it's a straight screw with the right installation torque. So this torque, if you don't know where to find this, is not now the time to see it. There is specific documentation on where to go and find the installation torque in case you can reach out and we can speak about this, but it's not now the time to go and check exactly which are the data. But just know that 40 Newton meter for a 12 for a HPS plate, so for a screw, for a partial thread screw for plates, diameter 12, this is the right torque. On the bottom here, there are 3 repetitions. Everything is green. It means that after 23 days, we didn't have any failure. So each one of these, it's a line, it's a test. So these are 3 screws installed in this way, and for 23 days, they didn't break. These in green, the numbers here are the moisture content average of the piece of timber here. So there are no failures with the right installation, with the right angle, and with the right torque. But what happens when we start to have an inclination, like we saw in the beginning, right? In the first picture, we had a very evident installation issue. With an installation and with a bad installation, with an angle installation, and also with double the torque, so 80 Newton meter, so double the torque that you should install the screws, you see that 2 out of 3 connectors failed. Also the third one should have failed. So probably there was something that didn't work out well, and actually in the end this didn't fail, but actually this also most likely would have failed just maybe briefly after the last day. There is some variability, of course, in this type of test. So what is critical here is that with a thick plate, with a wrong installation, and with a bad angle of installation, it's very likely that we go to break the fasteners. And if you think that this installation torque is too high and it's impossible to apply it, this is not true. It's very easy to over torque and to crash against the steel plate. It's very easy with an impact drill. With an impact screwdriver, it's very easy to just crush it and over torque the fasteners. Okay. This was made, so again, sorry, let me go back. This test was made for many configurations, not only for this one. So the baseline was made, and then also a lot of different cases. Okay, but how much is the tension generated in the screw axis when we over torque? This is what we wanted to try here. And in this case, this piece of timber is made again with load cells inserted in these small circular millings. And again, when we over torque. So when we apply a torque that is too high, so this one on the left between 68 and 68, 67 of installation torque. Actually, this is the amount of tensile stress that you get, so upon force that you get on the fastener. So this is for one fastener. So the amount of stress, of actual stress that you get due to the installation is pretty high. So this amount of stress, it's easily the same amount of stress that the screw itself can withstand. It is, if you go on and check how much is this stress compared to the steel itself, so compared to the steel tensile resistance of the screw of the fastener, you will see that just with the wrong installation, you are already using all of the resistance in tensile of the fastener itself. And this is very critical. So it means that we are installing things, and due to the bad installation, we are already at the maximum resistance in tensile stress for the screw itself. It means that there is no buffer, there is no safety if something else happens. For example, a water issue, like we just saw before. So the water is a topic, and then the installation is another topic, and also the angle of installation that we do not want to have that angle. So again, making a summary, let's say, we have the force that we have to design. We have the design for. We have the over torque that generates an additional tensile stress. We have the load caused by the wood swelling. All of these should now be lower than the resistance of the fastener itself. So this is the reason why sometimes we get questions about maybe some connectors failing, and then we go on site and we find that the team used impact drills without stopping on the plate, and then we also find a lot of water on site. So we have to be careful about this. Another topic that is brought up pretty often when we speak about this topic is that one could also say, yeah, but the issue is not the design. Of course, many designers sometimes they will say, no, but the issue is not in the design itself. Sometimes we get this type of complaints, and the installers or the design studio will say, no, but the issue is on it's an issue, it's a product issue. So usually there are these words that come out that are hydrogen embrittlement. Hydrogen embrittlement can be of internal sources. So during the production, the internal hydrogen embrittlement failure only happens in the first few hours or days after the installation. So if the issue is the hydrogen that was trapped in the connector due to the production phase, so it means that it's a product issue, it has to fail in the first few days, maybe 1 week. But in most cases, the issue is the environmental hydrogen embrittlement. So it means that there is hydrogen coming from the corrosion. So could be the byproduct of a corrosion process, or just could be even some water just present on site. These, together with all of the other factors that we just saw before, this could mean that you could reach a failure due to the fastener breaking in a brittle way. It's a combination, between all of the things that we just saw before, and also could be also caused by one of these two hydrogen embrittlement failures. So again, everything, as I just said, is a combination of things. So The first combination is to have a pretty high hardness connector. So if the fastener is it's a high hardness connector, if there is a sustained load, and if there is an hydrogen source, the combination of these could lead to a failure due to hydrogen embrittlement, which again has to be divided into internal and external environmental. In the initial part today, we saw these four voices, right? The continuous stress, the overtorquing, the bad installation. So today we're not covering the part about the core hardness. Anyway, when we have a failure due to these reasons, it means that it's a combination of all of these factors. Hydrogen, usually the internal, again, is the one that has been englobated in the structure of the fastener, along the grains of steel, and then a small crack could open on the body of the screw, and then it means that if there is tension, the screw will crack on that point and then open up. Usually we want to avoid this, and in order to avoid this, there are special precautions applied on the fasteners, especially today. The latest, let's say, the latest standards are speaking about having at least a core hardness below 390. Actually, even better is to have a core hardness below 360. For the environmental source, hydrogen source, it means that it's something that is in the environment. So it means that it could be water, also could be corrosion present in the zone of the fastener. And then again, this can lead to unexpected failure if there is a sustained tensile force. Again, so we just saw all of these three protagonists of this talk: the overtorque, the swelling, the misalignment, and then also we want to add this factor. So if we have high hardness screws, this could also increase the percentages of failure in case. This is more critical. This is mostly critical in steel to timber. It is not as critical in timber to timber, because if you have timber to timber, even if one element swells, if it's timber to timber, the counterpart is not as rigid as a steel element. So this is only applied. So these ideas, this webinar is only applied to timber to steel connection. For timber to timber, this is something that usually does not happen. It could happen in some special cases if we have a lot of swelling and fasteners that cannot move at all. Then this could also happen in a timber to timber connection, but usually this is limited to steel to timber. Also because, again, the impact drill issue that we just spoke about before, so arriving on the steel plate with maximum force, usually cannot happen on a timber to timber connection. Usually they happen on a steel to timber connection. So the designer task is to, usually what we suggest to do is to prefer screws with a larger diameter. You could also just reduce the length and increase the diameter to reach the same resistance. But if we have a shorter screw, it means that we are not taking as much swelling into the fasteners, because shorter screws with it will mean that we have a lower depth in timber, so the swelling is not as impactant on the fasteners. So we want to prefer larger diameter fasteners and maybe shorter, compared to, instead of lower number of fasteners but longer. We can also add damping systems, so a buffer, so a compression material to absorb some compression. This is being already done when someone has a structure completely outside, exposed to the weather. Sometimes some designer already they specify, they design a small, a few millimeters layer of resilient material, so like a rubber material or an APDM material to take some of this compression. And also we always want to avoid details that that prevent water drainage. So we want to have water drainage. We want to have water to go away. It is not an issue to have water for just a few hours. It's an issue when water is present on site for a lot of hours together, right? The installation has to be correct without overloading the connections. We want to make the pilot hole. We want to make the pilot hole also to have the right direction. And we want to have no impact drill, and also no impact drill only in the last point when we touch the plate. You can use the impact drill just as long as you stop before reaching the plate. Protect the connection from water and install the wood members with a moisture content close to that of service. Just a quick video that we can look together of an installation with this is an inclined washer. This is a jig, so it's a small jig in order to make a pilot hole with the right inclination. So this one is the washer inclined 45 degrees. This one, the darker one, is a small jig in order to make the pilot hole. Why do we make the pilot hole? We want to make the pilot hole in order to have then a perfect, with the right inclination, installation. You see, he stopped just before reaching the steel element, and then you finish it with a torque wrench. The torque wrench will have to be set to the right insertion moment, and then this is the right installation. Okay, this is it. We are just a little bit, let's say, shorter in time. So it's just around 40 minutes, but I don't think there are many other things to say. I don't know if Chris, if we have questions here in the chat, if we can, if you can check them.
Yep, let me look. I don't see any questions at this moment in time. So for now, we will just say thank you all for attending the webinar today. If you do have any questions at all, the email that's on the screen currently, eng.na@rotherblast.com, is the best email to contact. Whether those questions come on in the next hour, day, week, or even month or longer, feel free to reach out to us and ask any questions. And then just for everybody's knowledge, we do have a few more webinars coming up throughout the rest of this month. Next week, we have our webinar on our brand new USA specific screws catalog. If you register and attend, you can secure 15% off your next order up to $1,000. And then on the 16th, we have innovative connection for mass timber, covering the radial, the disc, the ring, the uplift, the spider, and more different products on the cutting edge connectors and systems for architect, engineers, construction professionals. On the 23rd, we have digital design tools for modern timber construction with Generate. And the last part of the month, for the 30th, it's a focused case study on the Alumega pin connection for post and beam systems. So thank you again, and we wish you all a happy week.